In this video, I am going to discuss some PYQs of isomerism. So this is part 1. Here the first question is, which of the following does not show geometrical isomerism? He has given 4 compounds. Instead of giving the structures, he gave IUPAC names. 1,2 dichloro 1 pentene, 1,3 dichloro 2 pentene, 1,1 dichloro 1 pentene, 1,4 dichloro 2 pentene. And you can see these are the structures. The first one 1,2 dichloro 1 pentene. So here you can see this carbon and this carbon. Here this is chlorine, hydrogen, chlorine and N-propyl group. So this is A, B, A, D structure. So it shows geometrical isomerism. But the question is, which of the following does not show? The second one, if you see, the name given is 1,3 dichloro 2 pentene. 1,3 dichloro 2 pentene. This is the structure. So this is a double bond, and here the carbon, this is hydrogen and CH2Cl, and this carbon has a chlorine and ethyl group. So this is A, B, D, E structure. It also shows geometrical isomerism, but here we use EZ nomenclature. And the third one is 1,1 dichloro 1 pentene. So this is 1,1 dichloro 1 pentene. But most importantly, this particular carbon, both are chlorines. So this molecule does not show geometrical isomerism. So answer must be C. So this is a single correct. So obviously you need not to check option D. Even if you see option D, here this is double bond, double bonded carbon, hydrogen, CH2Cl, hydrogen, CHCl, CH3. So this is A, B, A, D structure. It also shows geometrical isomerism. So the answer will be C. Among the following 4 structures, 1 to 4, 1, 2, 3, 4 structures are given. And here he is asking the correct statement, which statement is true. All 4 are chiral compounds. Chiral compounds, so chiral compounds rotate plane polarized light. So in the first question, in the first option, if you see there is a chiral center, so due to the presence of chiral center, this particular molecule is chiral. So the compound containing one chiral center is always chiral. And the second one, here also you can see this is a chiral center because it has ethyl group, methyl group, ethanoyl group, hydrogen. Molecule with one chiral center is always chiral. And in case of third one, there is no chiral center, it is carbocation. Even in case of fourth one, there is no chiral center because this is having ethyl group, ethyl group. Even in this ethyl group also there is no chiral center. So 3 and 4 do not have chiral centers. So obviously 1 and 2 are chiral molecules. So the answer must be B. So molecule with one chiral center is always chiral. Next, let us move on to the third question. On mixing certain alkane with chlorine and irradiating it with ultraviolet light, it forms only one monochloroalkane. That alkane could be. So we have to verify the options. So the first one is propane. When it is subjected to chlorination in presence of sunlight, here the possible products, this is 1-chloropropane and 2-chloropropane. We are getting 2 products. But the question says only one product, so A is not your answer. Next, B, if you take a pentane, in case of pentane, so totally when it is subjected to monochlorination, so this also gives more than one, but let us solve this question. 1-chloropentane, 2-chloropentane, 3-chloropentane. So if you take the structural isomers, we are getting 3. But here if you include chiral center of stereoisomers, here there is one chiral center. Therefore, one enantiomer will be obtained. So structures, at least if you take, you are getting 3 structures. Next one, isopentane. So here this is isopentane. the structure of isopentane. This is the structure of isopentane when it is subjected to monochlorination. This carbon and this carbon both are structurally same. Therefore, you do chlorination there, here or here, the result is the same. And another possible structure is this one. Next possibility is this one. And of course, here one more possibility. These are the structures. We are getting 4 structures, but he is saying only one. And the last one, that is neopentane. In case of neopentane, so this is the structure of neopentane. So all these methyl groups are identical. For your convenience, let me write the elaborated structure. So this is neopentane. IUPAC name is 2,2 dimethyl propane. When this is subjected to monochlorination, so these 4 methyl groups are identical. You do chlorination anywhere, the result is the same. Only one product, even there is no chiral center, so only one product is produced. The question also says the same thing, only one monochloroalkane, so the answer must be D. Fourth one, which of the following will have mesoisomer also? Mesoisomer. Compound with one chiral center is always active, there is no meso compound. And the compound containing 2 or more chiral centers and which is optically inactive, that is having plane of symmetry or center of symmetry, so that is meso compound. So let us take the options here. 2-chlorobutane. In case of 2-chlorobutane, there is only one chiral center, so this is always active. So here there will be no meso compound for this. Next one, 2-hydroxypropanoic acid. 2-hydroxypropanoic acid. So lactic acid, here also only one chiral center, therefore it will not have meso. 2,3-dichloropentane. 2,3-dichloropentane. Of course, it has 2 chiral centers, but this chiral center and this chiral center, these 2 chiral centers are dissimilar. The molecule is unsymmetrical. The molecule is unsymmetrical, therefore there is no question of having plane of symmetry. So this is always optically active, no meso. And in case of option D, 2,3-dichlorobutane. 2,3-dichlorobutane, if you see this particular example, there are 2 chiral centers, and here these 2 are similar chiral centers. In one of the stereoisomer, the 2 chlorines will be like this. So here this is one stereoisomer and it has a plane of symmetry, so this is optically inactive. The molecule containing 2 or more chiral centers and optically inactive, that is called meso compound. So obviously the answer will be D. Answer is D. Next one. Among the following compounds, the optically active alkane having lowest molecular mass. First thing, it must be alkane and it should have lowest possible molecular mass. So straight away B is ruled out because it is alkyne, and remaining we have to check alkane, cycloalkane, derivative, whatever it may be. It should be optically active, so there must be at least one chiral center, but in the first one there is no chiral center. There is no chiral center, therefore it can't be your answer because it is optically inactive. And here also there is no chiral center because this is not a chiral center. Here we have methyl group, here methyl group. In ethyl group also there is no chiral center. This is not a chiral center, so this is not having chiral center. And obviously only one option you have, that is option D. Here you have chiral center, this one. This is having one chiral center. You can see ethyl group, methyl group, hydrogen, another one is isopropyl group. So answer must be D. Next one, which of the following compound is not chiral? Which of the following, chiral is optically active, which of the following is not optically active? Molecule with one chiral center is always optically active. We have to verify the options. 1-chloropentane. 1-chloropentane, there is no chiral center. Which of the following is not chiral? So definitely there is no chiral center. Therefore, this is not chiral. So first option 1-chloropentane. Let us verify. Already we got the answer. Let us verify the remaining options. 3-chloro 2-methyl-pentane. So this is pentane. 2-methyl 3-chloro. Yes, you can see there is one chiral center. So there is one chiral center. Therefore, a molecule with one chiral center is always chiral. And option C, 1-chloro 2-methyl-pentane. 1-chloro 2-methyl-pentane. Again here there is one chiral center. So this is always chiral. And option D, 2-chloropentane. 2-chloropentane. And even here there is one chiral center. Molecule with one chiral center is always chiral. So answer must be, which of the following compound is not chiral? So answer is A. Next one. Of the 5 isomeric hexanes, the isomer which can give 2 monochlorinated products, which can give 2 monochlorinated compounds. So let us take up the first option, N-hexane. Totally 6 carbon atoms are present. Monochlorinated products. So this is 1-chlorohexane, 2-chlorohexane, 3-chlorohexane. Even if you write chlorine here, that is 3-chlorohexane. If we do not include stereoisomers, already we got 3 structures. It is not a total number of isomers. Don't be confused. 3 structures we are getting, but he is saying only 2. So A is not your answer. B, 2,3 dimethyl butane. 2,3 dimethyl butane. So these 4 methyl groups are identical. You write chlorine here, or here, or here, or here, the result is same. You write chlorine here or here, the result is the same. When it is subjected to chlorination, so here this is chlorine, one structure, and here this is chlorine, 2 structures we are getting. But most importantly, there is one chiral center, but he didn't mention only structures. Therefore, we have to check the remaining options also, because if we incorporate stereoisomers, we are getting 3 because there is one chiral center. So let us verify the remaining options also. 2,2 dimethyl butane. So you do here or here or here, the result is same. Here the result is different. Here the result is different. Here you are getting 3 structures. So structural isomers we are getting 3. This is the second one. This is the third one. Of course, here we have chiral center. If we include stereoisomers, totally we are getting 4. So this is structures, 3 structures it is providing. 2-methyl pentane. This is 2-methyl pentane. When it is subjected to monochlorination, this one and this one result is same. 1, 2, 3, 4, 5 structures we are getting. 5 structures. So this is the first one, second one, third one, fourth one, fifth one. But of course here, if we take only structures, then answer B, So that is 2, 3 dimethyl butane. So answer must be B. Only structures if you take, we are getting 2. The next one, which types of isomerism is shown by 2, 3 dichlorobutane? 2, 3 dichlorobutane. And here we have one chiral center. Here we have one chiral center. So here, which type of isomerism is shown by 2, 3 dichlorobutane? Here the positions are fixed, so you cannot write the structural isomers. There is no geometrical center. Geometrical isomerism is not possible. There are 2 chiral centers, therefore it shows optical isomerism. Tautomerism, there is no enolizable hydrogen, so tautomerism is also not possible. So the answer must be B. So answer to this question is B. Next one, increasing order of stability among the 3 main conformations eclipsed anti-gauche of 2-fluoroethanol. 2-fluoroethanol. So this one, here he is asking eclipsed, anti-staggered and gauche staggered. So this is one carbon, this is another carbon, one is near carbon, another one is rare carbon. So let us write the conformations first. This carbon is having 2 hydrogens and fluorine. This carbon is having 2 hydrogens and OH group. OH group, hydrogens. And here the next conformation, in order to get the next conformation, so this rare carbon is rotated. If you rotate 60 degrees, you will get eclipsed conformation. So here it will be, but here I am rotating 120 degrees. 120 degrees I am rotating. So this is OH, fluorine, hydrogen, 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 hydrogen. If you rotate 60 degrees, you will get eclipsed conformation. But of course, he didn't mention fully eclipsed and partially eclipsed. So here this is fluorine, OH, hydrogen, 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 hydrogen. Here this is anti-staggered and this is gauche staggered and this is eclipsed. Anything eclipsed is unstable. Anything staggered is more stable. Here the question is about stability, and most importantly eclipsed is least stable. But in case of gauche staggered, there is intramolecular hydrogen bonding. Due to intramolecular hydrogen bonding, gauche staggered is more stable. But one more important point, he is asking increasing order of stability. So first here, increasing order of stability, you have to start with the sum which is having least stability. So eclipsed, anti-staggered and gauche staggered, this is the order of stability because he is asking increasing order of stability. So eclipsed, anti-staggered and gauche staggered, so the answer must be C. So the correct answer to this question is C. And the next one, which of the following molecule is expected to rotate a plane polarized light? Simply he is asking which of the following molecule is chiral. Molecule with one chiral center is always chiral. Symmetrical molecules with 2 or more chiral centers having plane of symmetry, they are achiral. If you see the first one, there is only one chiral center. Which of the following molecule is expected to rotate a plane polarized light? Definitely A rotates. But here this is achiral because there is no chiral center. But in the next one, if you see, there is a plane of symmetry. If you cut the molecule like this, it is divided into 2 equal halves. And of course, it is having POS, it is meso structure. This is optically inactive. So this is achiral. And the next one, there is no chiral center. Therefore, it is also achiral, and that is glycine actually. So which of the following molecule is expected to rotate a plane polarized light? So the answer is A, glyceraldehyde, that is. Now let us move on to the next question. Here the question is, which one of the following conformation of cyclohexane is chiral? He is asking about the chiral conformation of a cyclohexane. Here the options, if you see, the first one is a twist boat, second one is rigid, third one is a chair, and fourth one is a boat. In these four, straight away one is eliminated as such, that is rigid. In fact, there is no conformation of cyclohexane with the name rigid. So we don't have any conformation of cyclohexane that is rigid form. So twist boat, chair and boat, these are the things we have to consider. So here the first conformation, this is a chair conformation, and if you pass the plane through 1 and 4 carbons, you can take this one and this one, or this one and this one, or even this one and this one. If you cut the molecule like this, that is going into the plane, so here like this, so that is passed like this. Now what happened, that particular molecule is divided into two equal halves. So chair form of cyclohexane has a plane of symmetry, therefore this particular conformation is achiral. This is optically inactive. Next one is boat form. So here this is the boat form, and if you cut the molecule like this, again it has a plane of symmetry, therefore this is also achiral. But if you take the twist boat conformation, this is the front side part and this is the back side part. So here if you pass the plane through 1 and 4 carbons, so here this is the front side part and this is the back side part, there is no POS, therefore this particular thing is chiral. It is satisfying the definition of chiral molecule. So which conformation of cyclohexane is chiral? So the answer must be twist boat. So that is A. And the next question is absolute configuration of one molecule. Here it is a dicarboxylic acid, basically it is a tartaric acid. This is one chiral center, this is another chiral center. But most importantly, while giving RS configuration, absolute configuration, we have to see that the least priority group should be away from the observer, but here that is at wrong position. So first let us give the priority. This is one chiral center, OH gets first priority. CIP rules I am considering. COOH gets second priority, and this bulky group gets third priority. Hydrogen gets fourth priority. Here fourth priority, hydrogen is at correct position. You are moving in clockwise direction, so at this carbon the configuration is R. Now this is the chiral carbon, we have to predict the configuration. Now what I am saying is, for the sake of convenience, so this is COOH, this is OH, and this is hydrogen, and this is a bulky group in the sense this entire group. I am writing it as a G. And if you see the priority, CIP rules if you apply, OH gets first priority, COOH gets second priority, that group gets third priority, hydrogen gets fourth priority, but least priority group is at wrong position. So what we have to do, we have to do some operation. As a result, we are going to get a opposite configuration, reverse after operation. So we are going to interchange the position of these two, odd number of changes. We are making one exchange, one interchange, whatever it may be. So configuration is inverted. So inverted configuration due to that exchange. So OH gets first priority, COOH gets second priority, group gets third priority, this is getting fourth priority. Now this is the correct direction. You are moving like this. You are moving in anti-clockwise direction. So therefore that configuration is yes. So due to this interchange, the configuration is inverted. After inversion, the configuration is yes. Therefore, before inversion, the configuration would be definitely R. So this is R, this is also R. Both are having the same configuration. So this is RR configuration. So answer must be B. Next, the alkene that exhibits geometrical isomerism. And here geometrical center is present or not. In this example, this is geometrical center. You can see hydrogen and methyl group, hydrogen and methyl group, AB type of structure. So definitely 2-butene shows geometrical isomerism. We got the answer actually. So this is not a geometrical center because here the groups are repeated. This is also not a geometrical center because hydrogens same here repeated. Even here this is not geometrical center. Here hydrogens are repeated. Here methyl groups are repeated. So answer must be 2-butene. In the next question, the number of stereoisomers possible for a compound of the molecular formula CH3 CH double bond CH CHOH methyl, like this. So in this we have one geometrical center and this is chiral center. So in this example, so this is geometrical center and this is optical center. One geometrical center, so here cis and trans isomers are possible. One optical center, R and S are possible. Totally here we can simply say 2 power 2, 4 isomers are possible. What are the 4 isomers? If you see cis R configuration, cis S configuration, trans R configuration, trans with S configuration. So this is the configuration of geometrical center. This is the configuration of chiral center. Totally 4 possibilities. So the answer must be 4. So answer is A. Next one, identify the compound that shows tautomerism. Tautomerism. Enolizable hydrogen should be present. So here there is no enolizable hydrogen. Lactic acid, 2-hydroxypropanoic acid, no enolizable hydrogen. Pentane 2-one, CH3, C double bond O, CH2, CH2, CH3. Here tautomerism is definitely possible. So here this is hydrogen enolizable. This is also enolizable hydrogen. So 2-pentanone. And of course phenol. Here we have enolizable hydrogen, but the percentage of enol form is more, nearly that is 100%. But in this case, 2-pentanone case, we have enol form and keto form. So however it is a single correct, we have to go for the best option, that is 2-pentanone. Phenol has ability to exhibit tautomerism, but here the percentage, if you compare, almost 100%. So this one and this one, if you compare, here nearly we get 100%. So the best option is 2-pentanone. How many chiral compounds are possible on monochlorination of 2-methyl butane. This methyl group are identical. You will get the same structure. This will give different one, this will give different one, this will give different one. First, let us write all possible structures. Then we'll check for chirality of the molecule. So this is the second structure possible. This is the third one. And this is the fourth one. And in the first example here there is one chiral center. In second example there is definitely no chiral center because this is methyl group, this is methyl group. And in the next third one, yes, here we have one chiral center. Third one, chiral center. Fourth one, there is no chiral center. So it has one enantiomer. It has one enantiomer. So first one, it's enantiomer. This will be third now. Fourth one, and it's enantiomer. And here this is the sixth one. So answer must be D. Which branched chain isomer of hydrocarbon with molecular mass 72 gives only one isomer of monosubstituted alkyl halide? So here he is saying hydrocarbon, but here in the first option tertiary butyl chloride they gave, so straight away that is ruled out. And you have to take the molecular mass 72, it must be isohexane. Neopentane, pentane, basically that is pentane, neopentane, so that is C5H12, neohexane C6H14, and here the molar mass is 84, here the molar mass is 72, here the molar mass is 84, so these two are also ruled out. So the only option remaining, that is C5H12, so that is neopentane. But of course, at least we have to prove that on monochlorination, this will give only one monochlorinated product. You can see all methyl groups are identical. You can do substitution anywhere, the result is the same, and even there is no chiral center. So the answer must be B, neopentane. The absolute configuration, here the molecule is represented in Fischer projection formula. So there are two chiral centers. Here COOH, OH, chlorine, CH3, hydrogen, hydrogen. So this is numbering, IUPAC numbering, if you see first carbon, second carbon, third carbon, fourth carbon. So this is one chiral center, this is one chiral center, second carbon is one chiral center, third carbon is one chiral center. So first let us take CIP rules. OH gets the first priority. Next here if you see, this is carbon, this is carbon. When first element is the same, we have to consider the second elements, oxygen, oxygen, but here we have chlorine. So this bulky group gets second priority, COOH third priority, hydrogen fourth priority. Remember, hydrogen is at wrong position. So you have advantage in Fischer projection formula, need not to make any operation. You just connect 1 and 2 groups. You are moving in clockwise direction. Obtained configuration is R, but here hydrogen least priority group is at wrong position. Therefore, we have to reverse the configuration. You are moving in clockwise, you are getting R configuration, but you have to take the reverse configuration. Therefore, at second carbon, it has S configuration. This is ruled out. This is ruled out. Now let us take at third carbon. So here chlorine gets the first priority. That bulky group gets second priority. Methyl third. We are giving configuration at this chiral center. No confusion. for your convenience. So here this is chlorine, methyl group, hydrogen, and this group. You just observe only this carbon, right? Chlorine first priority, that group gets second priority, methyl third priority, hydrogen fourth priority. And again hydrogen is at wrong position. You are moving in clockwise direction. Obtained configuration is S, but the original configuration will be R. So that is 2S 3R. So the answer must be B. The next one, in the following structure, the double bonds are marked as 1, 2, 3, 4. Which double bonds is or are capable of showing geometrical isomerism? So which double bond is geometrical center, he is asking. Here if you see, this is methyl group, this is methyl group. So definitely this is not a geometrical center, first one. And here we have methyl group, this group is different, methyl group and hydrogen different. So this is a geometrical center. And here methyl group and this bulky group, methyl group and this bulky group, ABAD type of structure. So this also shows geometrical isomerism. And here this is, yes, methyl and ethyl, methyl and some bulky group, it also shows. So answer must be 2, 3, 4. 2, 3, 4. Next, the number of chiral carbons present in the molecule given below. Chiral carbons, sp3 carbon with 4 different groups. So it is satisfying the definition. sp3 carbon with 4 different groups. Forget about all these carbons because they are sp2. Even ignore these, they are sp2. This is also ignored because that is also sp2. This is ignored because hydrogens are repeated. Now, it is satisfying the definition of chiral carbon because it is sp3 hybridized. This group is different, this group is different, this is different, another one is hydrogen. And this is also chiral center. 4 different groups it has. And here if you see this particular one, this is also chiral center because it has ethyl group, hydrogen. Here we have CH2, immediately nitrogen, but this side we have some carbon chain. Therefore this is also chiral center. This is not a chiral center, that is CH2. Now this carbon if you take, I am not taking this one because it is CH2, CH2, CH2. This is also CH2, but this one if you see, this is chiral center. If you have any confusion, you can see this is CH2, CH2 nitrogen. Here this group is different because it is not CH2, CH with ethyl group. So this is different, this is different. This is also different because it is CH2. After that it is connected like this, and another one is hydrogen. So this is also chiral. So ultimately 1, 2, 3, 4, 5. So let us move on to the next question. In this question, he is asking the number of chiral centers present in 309. Here the number of chiral centers and the molecule is 309. Here I just wanted to mention one point. In that question they didn't give the structure of 309. The student has to learn the structure of 309 in one chapter, that is amino acids, which is the last chapter, that is biomolecules in the entire organic chemistry. But for time being I have given the structure. You just identify the number of chiral centers. So here chiral centers, sp3 hybridized atom with the 4 different groups, that is called chiral center. And in this example, so here this is sp3, this is sp3, this is also sp3. Of course here nitrogen and oxygen are also sp3, but there are no different groups attached to nitrogen, so obviously that is not a chiral center. Now let us check. So this particular carbon is a chiral center because it has a COOH, NH2, and here this is a hydroxyethyl group and hydrogen, 4 different groups. It is satisfying the definition. And the next one, this carbon is also chiral center. If you see the groups attached to this, one is a hydroxy group, methyl group, hydrogen, and here this bulky group. Totally 309 has 2 chiral centers. In the next question, among the following compounds, geometrical isomerism is shown by. Here you need to know the different geometrical centers. Let us observe all the options 1, 2, 3, 4. Here in this example, this double bond is a geometrical center because this carbon has hydrogen and chlorine. This carbon has these two groups which are different. Maybe you are getting confused by seeing these two groups, but continuation you have to see. Next we have a secondary carbon, but here we have tertiary. Not only these two carbons, there is a continuous chain. You have to consider the remaining part as well. Here we have a CH2 which is a secondary carbon. Here we have tertiary carbon. So this carbon is satisfying the condition. This carbon is also satisfying the condition. So this is a geometrical center. So first one shows geometrical isomerism. Second one does not show geometrical isomerism because these two groups are identical. So the second one does not show. Third one, maybe you are considering this part. Of course, this is not a geometrical center, but this is a geometrical center. Double bond is not geometrical center. Here the ring system, the rigid ring is a geometrical center. So third one shows geometrical isomerism. And if you see the fourth one, so here this is definitely not a geometrical center. Double bond is not a geometrical center because these two groups are absolutely same. So the answer must be 1 and 3. So answer is 1 and 3, that is option B. Which of the following compound shows geometrical isomerism? Geometrical isomerism is shown by which compound? So we need to draw the structures fastly. So this is first option, basically that is pentene, 1, 2, 3, 4, 5, pentavanine, and here it is 4-methyl. Need not to write the complete structure. You can see here hydrogens both are same, so it is not a geometrical center. So double bond is not a geometrical center, so the first one does not show. Second one, 2-methyl pentatoluene group. These two groups are same, therefore this is not a geometrical center. Second one does not show geometrical isomerism. And third one, 4-methyl pentatoluene. So here again this is a pentatoluene. So this is a second carbon. There is a double bond. 4-methyl. This is a 4-methyl group. At the fourth position there is a methyl group. And here if you see, this is a hydrogen and this is methyl. Here we have hydrogen and this is isopropyl. If you carefully observe, hydrogen and methyl, hydrogen and isopropyl, ABAD type of structure. So it shows geometrical isomerism. Since it is a single correct, need not to check the fourth option when you are writing exam. That is only to save the time. So but here let us check fourth one also, 2-methyl pentavanine. So here basically this is also pentene, pentavanine. Once you are saying, and methyl group is at the second place, and here this carbon, double bonded carbon. So here the two valencies are satisfied by same element, that is hydrogen. So this is not a geometrical center. So fourth one also does not show geometrical isomerism. So answer will be 3. Here, the compound with the molecular formula C3H6O. C3H6O. Here I don't want to waste the time. So degree of unsaturation, that is double bond equivalence. So here that is equal to 1. Double bond equivalence equal to 1. So it can be either aldehyde or a ketone. So first let us check. positional isomerism. Whether it can show positional isomerism or not, we have to check. So in case of positional isomerism, degree of unsaturation is 1. We can write a open chain compound and also cyclic compound. If you take open chain compound, we have to write a aldehyde, and if you write another one, that will be ketone, and these two are functional group isomers. But what about a cyclic structure? So let us write the cyclic structure. It can be a cyclic alcohol as well. And here OH group, even if you shift the position of OH, it is not a positional isomer because all 3 carbons of cyclopropane are same. Of course, you may be thinking about this, but here these two are again functional group isomers. So positional isomerism is not possible. Positional and metamerism, definitely not possible. Only metamerism, also not possible, because ketone, in order to exhibit metamerism, it has to have minimum 5 carbons in case of ketones. Functional group isomerism, yes, it can show functional group isomerism. We can write aldehyde and ketone, cyclic alcohol and cyclic ether as well. So the answer will be D. And in the next question, which one of the following pairs of isomers is an example of metamerism? So you just try to recollect the definition of metamerism. So the structural isomers which differ in alkyl groups attached to functional group. So alkanes, definitely they never exhibit a metamerism. In fact, here these two, 1, 2, 3, 4, 5, these two are chain isomers, and here this is ketone and this is aldehyde. If they have same molecular formula, so here this is a phenyl group and 2 carbons, phenyl group and 3 carbons, they are not at all isomers. Next, option 3, if you see, so alcohols do not exhibit, and here this is ketone. So here this is having ethyl group and butyl group, but here both the sides it is having propyl groups. So this is an example, this pair is an example of metamers. Next, find the total number of acyclic isomers. Acyclic isomers, open chain compounds is asking. C5H10, C5H10. One more important point, he is asking total. Total number means we need to consider structural isomers and stereoisomers. Be very careful. C5H10, degree of unsaturation, that is double bond equivalence is equal to 1. So we can write a double bond, but we are not going to write a ring system because here the question says only acyclic isomers. So this is 1, 2, 3, 4, 5, pent 1 in, 1, 2, 3, 4, 5, pent 2 in, and even if you shift the double bond to this position, that becomes a pent 2 in only. So first I will write all the structures, then I will incorporate stereoisomers. Let us move on to 4 carbon chain. 4 carbon chain, double bond at this place, methyl group is here. Again 4 carbon chain, double bond at this place, methyl group is here. So don't dare to put methyl group here, because if you put methyl group here, these two will be same. So even you cannot write methyl group at a terminal position, terminal carbon, that will be coming into the longest chain. Now let us shift the position of double bond as well, like this, and you can write methyl group here or here, the result will be same. So this is methyl group, and these are the 4 carbon chain, 5 carbon chains and 4 carbon chains. Let us try to write a 3 carbon chain. Let us try whether it is possible or not. You have to put a double bond here. You need to put a double bond here or here, the result is same. Totally there are 5 carbons in the molecule. You are trying to write the 3 carbon chain. That means you need to put 2 substituents here. What I am saying is, if you write ethyl group here, that becomes a 4 carbon chain, but your intention is writing 3 carbon chain, that means here one methyl group, here one methyl group, but it is not possible because carbon is having 5 bonds. So 3 carbon chain is definitely not possible. Now here there is no geometrical center, but here there is a geometrical center. For your convenience, this is hydrogen, this is hydrogen, so there is one geometrical center, so plus geometrical isomer, that is diastereomer. One is cis form, another one is trans form. In the next one, this is not a geometrical center because this particular carbon is having hydrogens, so both are same, therefore geometrical isomerism is not possible. Even in the next example, geometrical isomerism is not possible. Chiral centers also we have to check. Of course, there is no chiral center. Even in the next example, you can see here, this is methyl group, this is methyl group, there is no geometrical center. So totally 1, 2, 3, 4, 5 and 6. So I am getting totally 6 isomers. Chiral carbons are also absent. Here the question is only acyclic isomers. Total isomers, acyclic isomers, answer must be 6. In the next question, the dihedral angle in staggered form of Newman projection of 1,1,1 trichloroethane. If this is the position of the observer and this is near carbon and this is rare carbon, so here this is near carbon and this is rare carbon. So here the groups are chlorines like this, and the rare carbon the groups are hydrogens, but he is asking staggered form. So this is hydrogen, this is hydrogen and this is hydrogen. He is asking dihedral angle, this is dihedral angle. One is attached to the front carbon, another one is attached to the back carbon. That angle is dihedral angle. If you take this one by mistake, that is not a dihedral angle, that is bond angle. So this is dihedral angle, this is dihedral angle, this is dihedral angle, but this is bond angle. So here dihedral angle rounded off to nearest integer, so the answer must be 60 degrees. Practically there may be slight deviation, but he is however asking round off to the nearest integer, that must be 60 degrees. And in the next question, arrange the following conformational isomers of N-butane in order of their increasing potential energy. It is not about stability, point number 1. It is not decreasing order, it is increasing order. So here you have one important relation, that is stability of a system is inversely related to potential energy. But here first you compare the stabilities, then you take the reverse relation. And actually, you know, stability order, if you take a stability order, anti-staggered, that is the most stable one. After that, Gauss staggered, that is the third one. And here we have something like this is Gauss staggered. Anything staggered is more stable. So this is eclipsed, this is also eclipsed, but this is partially eclipsed, it is fully eclipsed. So partially eclipsed is somewhat stable when compared to fully eclipsed. But here the question is not about stability, it is about potential energy. But don't forget, he is asking increasing order. So increasing order 1 less than 3 less than 4 less than 2. The one with the least stability will have highest potential energy. So here increasing order he is asking. So the answer must be 1 3. So 1 3 4 2. So the answer must be 4. Next one, identify the most stable conformer among the following. Of course, it is again the same question, that is N-butane. Most stable, so without wasting time, so anti-staggered is more stable, most stable is anti-staggered. Next, the isomeric deuterated bromide with molecular formula C4H8DBr having 2 chiral carbon atoms is. So first let us write the structures, whatever the options given. So the first one, that is 2 bromo 1 deutero butane, 2 bromo 1 deutero, and here this is not a chiral center because 2 hydrogens, and here this is chiral center, only 1 chiral center, but he is asking 2 chiral carbon atoms, so 1 is wrong. Second one, 2 bromo 2 deuterobutane, 2 bromo 2 deuterobutane, again there is only 1 chiral center, So this is also not your answer. 2-bromo 3-deuterobutane, butane derivative 2-bromo 3-deutero. Now this is one chiral center, this is one chiral center, so answer is 3. Let us check the fourth option as well. 2-bromo 1-deutero 2-methyl propane. Basically it is propane. First carbon deuterium, second carbon bromine, second carbon even methyl. Of course there is no chiral center at all, so here 0 chiral center, so it has 2 chiral centers, so answer must be 3. The next question, the total number of chiral compounds among the following. He is asking chiral compounds, optically active compounds. In this, if you see the first example, in case of this first example, this is not having any chiral center. Of course this is not a chiral center because these two groups are same. But in this what happened is cycloalkylidine, cycloalkane, that is the case it is. And here we have hydrogen, and this molecule, if you see, this part is in the plane of the paper, but there is no plane of symmetry. Here what happened is COOH is above the plane and hydrogen is below the plane. When you cut the molecule like this, when you cut the molecule, even if you take a paper plane, what happened, above you have a COOH and below you have a hydrogen. There is no plane of symmetry. Due to absence of a plane of symmetry, this molecule is chiral, optically active. In the next example, there is one chiral center. The molecule with one chiral center is always chiral. This is also optically active. In the next example, it is mesotartaric acid. There is a POS. Due to the presence of POS, it is achiral. Even if you see the next example, it also has POS. You can see if you cut the molecule like this, so here there is plane of symmetry. If you have any confusion, for your convenience, let me shift it like this, let me rotate it like this. Now you can see the plane of symmetry. If you cut the molecule like this, you can see the molecule is divided into 2 equal halves. Here we have OH below, here also OH below, here OH above, here OH above, here OH above, OH above. It has a POS, therefore this molecule is also achiral. Even if you see the last example, so it has plane of symmetry. Even though it has 2 chiral center, due to the presence of plane of symmetry, this is mesoform, I can say this is achiral. So he is asking the number of chiral compounds, so the answer must be 2, the first molecule and second molecule. Next one, testosterone, which is a steroidal hormone, has the following structure. He gave the structure. Find the number of asymmetric carbons, chiral carbons. sp3 carbon with 4 different groups. sp3 carbon with 4 different groups. Let us forget about this, because they are not sp3. Even methyl group let us ignore, because hydrogens are repeated. So this is CH2, we are ignoring. This is CH2, we are ignoring. This is CH2, this is CH2. Of course this is CH2, this is also CH2, we are ignoring. But if you carefully observe, this particular carbon has 4 different groups. You can check the 4 different groups. This is having 4 different groups. This is having 4 different groups. This is having 4 different groups. This is also having 4 different groups. This also has 4 different groups, but here we need to ignore because they are CH2 groups. Ultimately 1, 2, 3, 4, 5, 6. So it has 6 chiral carbons, testosterone. If you know the definition of chiral carbon, this question will be the easy one because the structure was also provided. In the next example, the total number of optically active isomers shown by C4H8Cl2 obtained in the following reaction. You are taking 2-chlorobutane. 2-chlorobutane, it is optically active. It is subjected to monochlorination. The procedure is very simple. First you write the all possible structures. Here chlorination I am doing. Here also we can do the chlorination. Dichloro derivative I am going to get. Even here a different structure we will get. Even here also we can. So these are the possible structures. Now here one chiral center, therefore plus enantiomer. Next one, no chiral carbon, no chiral center. Here there are two chiral carbons and the molecule is symmetrical. Totally 3 stereoisomers are possible. RR, optically active, its enantiomer SS, its diastereomer RS. Totally it will have additional 2 isomers, and here it has only one chiral center, therefore it has enantiomer. So answer will be 1, 2, 3, 4, 5, 6, 7, 8. But he is asking only optically active isomers. In this, one is meso, we need to ignore. Here there is no chiral center. This is also optically, that is not meso, that is optically inactive. So 8 minus 2, so the answer will be 6. Totally we are getting 8 isomers. 8 is not your answer because he is asking only optically active. The next one, total number of isomeric products formed by monochlorination of 2-methyl butane. This is 2-methyl butane and it is about monochlorination product, and I am not wasting time here. I am just writing the products directly. You can do here or here, the result is same. This is one possibility. Structures I am writing first. This is another possibility. This is one more possibility. Here this is a chiral center, one chiral center. Next second one, no chiral center. Next you have one chiral center. Next no chiral center. One chiral center plus enantiomer. Here also plus enantiomer. Total number of isomeric products 1, 2, 3, 4, 5 and 6. So answer must be 6. Number of optical isomers possible for 2-chlorobutane. There is only one chiral center. So 2 power n, it is unsymmetrical molecule. So n is number of chiral centers. So that is equal to 2. So one is dextroform, another one is levoform. So the answer is 2. Give IUPAC name of the compound, find the number of chiral centers, calculate double bond equivalence of the following. Of course, the question is about IUPAC, but I just wanted to discuss IUPAC name, number of chiral centers and double bond equivalence. IUPAC name. So this is the first carbon, second carbon, third carbon, fourth carbon, fifth carbon, sixth carbon, seventh carbon. And here this is a hydroxy group and this is a formyl group. They must be kept in alphabetical order. Hydroxy H formyl, F. So first we will say 2 formyl, 4 hydroxy, hept, 6 ene, 1 oic acid. Number of chiral centers. He is also asking number of chiral centers. So here this is one chiral center, this is one chiral center. There are two chiral centers. Double bond equivalents. So this is one, this is one, this is one. Totally 3 double bond equivalents. So chiral centers 2, double bond equivalents, degree of unsaturation, that is 3. And here there is a question, list 1, list 2, pair of compounds, type of isomerism, N-propanol, isopropanol. This is propane 1-ol, this is propane 2-ol, isopropanol. So they are positional isomers. Methoxy propane and ethoxy ethane. This is ether with methyl group and propyl group. This is ether with both ethyl groups. So this is example of metamerism. Here this is ketone and aldehyde. They are functional group isomers. Neopentane and isopentane, they are chain isomers. So A3, B1, C4. So answer is 4. Incorrect statement regarding geometrical isomers of 2-butene. 2-butene. It has geometrical center. Cis-2-butene and trans-2-butene are not interconvertible at room temperature. Yes. Stereoisomers, configurational isomers, which configurational isomers are non-interconvertible. So this is a correct statement. Cis-2-butene has less dipole moment than trans-2-butene. Actually, cis-2-butene has more dipole moment. Therefore, this is incorrect. So answer must be 2. Trans-2-butene is more stable than cis-2-butene. That is a correct statement. Cis-2-butene and trans-2-butene are stereoisomers. That is also correct statement. But he is asking incorrect statement. So answer must be 2. The possible number of stereoisomers of 5-phenyl pent 4-ene 2-ol. First let us write the structure properly. Pent 1, 2, 3, 4, 5. Pent 4-ene 2-ol. 5-phenyl. And here this is CH3, CH, CH2, CH, CH. Here there is chiral center, optical center, and here there is a geometrical center. So the molecule is unsymmetrical. So 2 power n, where n is sum of optical centers and geometrical centers. N value is 2. So 4 isomers are possible. They are chiral center configuration R, geometrical center cis, R, trans, S, cis, S, trans. So these are the 4 isomers possible. So let us move on to the last question in this part 1. Question number 40. Propane molecule on chlorination under photochemical condition gives 2 dichloro products. Dichloro products he is asking. This is propane. 1,1 dichloro, 1,2 dichloro, 1,3 dichloro, 2,2 dichloro. Actually we are getting 4, but he is saying 2 dichloro products X and Y. In X and Y, X is optically active. So here this is optically inactive, this is optically inactive, this is optically inactive. So here there is a chiral center. So this is X. How many trichloro products, consider only structural isomers, will be obtained from X when it is further treated with chlorine under photochemical conditions? So we are taking 1,2 dichloropropane. This is again monochlorinated. As a result, you are going to get a trichloro product. He is asking how many structures are possible. So chlorination on first carbon, chlorination on second carbon, chlorination on third carbon. You can do chlorination here or here or here, the result must be same. So here when we do 1,1,2 trichloro, 1,2,2 trichloro, 1,2,3 trichloro, so we are getting three structures, so answer must be 3.